Hey everyone, my name is Ilia. I'm from Intel VTune profiler team, where I'm responsible for platform I/O performance analysis. And today I'm going to talk about our brand new top-down topology-aware I/O performance analysis methodology of Intel VTune profiler. So this is a quick intro to make sure all of us are on the same page. Among applications running on Intel Xeon processors, there is a quite wide category of applications that are usually referred as I/O intensive, meaning that such applications are actively interfacing with various I/O devices like integrated accelerators or external PCIe devices like NVMe storage drives or network cards and so on. And in the big picture, performance issues of such I/O intensive applications might be categorized into three domains. The first one is called I/O device bound, and in this case, performance is limited due to device capabilities, and this is quite simple. Quite simple domain, and you just need to somehow capture performance numbers from the application level or from the platform level, and we will show how to do that with Intel tools, and then just refer to datasheet to make sure that your device is not hitting its limit. The other domain is called core bound, and in this case, performance is limited by algorithmic or microarchitectural code issues. And this domain is quite well covered with different core-centric analysis. For example, in VTune, we have hotspots, microarchitecture analysis, threading, Intel processor trace based, and so on, a lot of them. And the third domain, called transfer bound, is the one that I'd like to focus on today. And it appears most challenging because it used to be quite weakly covered with easy to follow methodologies, and it appears challenging because it happens. The performance in this case is limited by non-optimal interactions between devices and CPU, and multiple different agents are involved in this case. And in this talk, we'll see how to detect and address such issues using Intel VTune profiler. So this is the agenda that we have for today. We're going to see some architectural background, to see how I/O traffic is processed on the latest Intel Xeon processor. We will see what types of such platform level I/O traffic exist, which are Intel data direct I/O and MMIO traffic, and we will see how these two types are utilized in I/O intensive applications. And then we'll get down to performance analysis. We'll see how different metrics are implemented in VTune, and how platform level I/O can be analyzed with VTune. And eventually we'll see how to enhance this platform level view with some API level statistics for SPDK applications, and we will see how to get a better view on how software utilizes the hardware for SPDK application. Okay, let's start with architectural background. So this is how Intel Xeon Scalable processor looks like, the picture on the right. It is made by a mesh interconnect, which is the grid underneath on this picture. And this mesh interconnect connects various units on the chip. These units are the cores, and in Intel terminology, core means the term core covers execution units where your code is executed, and private caches, so L1 and L2 cache. And all the rest on the platform is usually referred as uncore, meaning like it is everything but not core. And there are a few different types of uncore units. Let me quickly walk you through these different types. So first of all, we have we have L3 cache controller, CHA, which is the coherence engine that manages a slice of L3 cache. L3 cache includes last level cache and snoop filter, and these units are placed all over the processor, basically next to each core on this picture. And also we have integrated memory controllers, which connect the processor to the DRAM. We have Intel UPI controllers, which make possible cross-socket interconnect. And eventually we have integrated IO controllers, which drive interactions between CPU and IO devices, internal devices like CBDMA, or external devices that can be plugged to the PCIe slots on the motherboard. So I'm going to focus on these integrated IO controllers as far as they drive each interaction between IO device and CPU. So in the third generation of Intel Xeon Scalable processor, there are up to 5 integrated IO controllers per socket. So 4 of these controllers serve as 16 lanes of PCIe Gen 4. And one manages CBDMA accelerator, which is the integrated accelerator for offloading memcopy in simple terms, and DMI interface that connects the processor to the platform controller hub. And the purpose of integrated IO controller is to translate the languages between PCIe domain and the mesh interconnect. So transactions that come from PCIe domain are translated into one or multiple cache line requests when the device talks to the CPU, and vice versa. Cache line requests are translated into TLPs when the CPU talks to device. So what types of these transactions that come through integrated IO controller exist? There are 2 types of them. The first one is called inbound, meaning that IO device requests something from system memory. For example, device might be reading this memory or writing system memory, and this type of transactions is traditionally called DMA, like direct memory access, and traditionally such requests go to the DRAM, to the system memory. But in Intel server architectures, the destination of such inbound transactions are the destination of such inbound transaction is L3 cache, and this is possible due to Intel DDIO hardware technology, which is transparent for the software. And the other type of transactions that go through integrated IO controller is called outbound. In this case, core reads or writes something from the device memory. So device memory is somehow exposed to the CPU and then mapped to the memory mapped IO space, address space. And when core accesses this address space, this read or write request is translated at the platform level into outbound PCIe transaction. So let's see what stands behind Intel Data Direct IO, like how it works at the platform level, and see what possible pitfalls might happen in the IO intensive applications. So inbound transactions, like I said, are routed directly to the local L3 cache, and there is a little difference between how inbound reads and inbound writes are processed on the platform. So when inbound read comes to the L3 cache, to the local L3 cache, the L3 cache lookup happens, and there might be two different cases. We may hit L3 cache or miss, and if we hit the cache, meaning that this data is already cached in the local socket, then it is just passed to the IO controller and then to the device. If we miss the L3 cache, then the data is found anywhere it is, like in local memory, in the remote cache subsystem, or in the remote DRAM, and then it is just passed again to the IO controller and to the device without local L3 cache allocation. The situation is a little bit different for inbound writes. So when device wants to modify the data, then it needs to get a copy of this cache line, and the cache line location is tracked in the L3 cache controller, so cache allocation is required. So inbound writes actually require cache allocation, and they get processed in two phases. At the first phase, IO controller just gets the ownership of the cache line, and then it is allowed to modify the data. And once the data is modified, IO controller sends the modified data back to the L3, and this phase is called write back phase. And this may happen in different scenarios depending on what configuration is chosen. So we may we may place the data in the local L3 cache, which is called allocating write back, or we may flash it to the DRAM. In this case is called non-allocating. So in any way, both reads and writes require the data. I mean, both reads and writes lead to the L3 cache lookup. So we may have two different scenarios from the performance perspective for both reads and writes. So this is the short, just short memo on how inbound reads and writes might be processed in the L3 cache. As I said, we may have either hit or miss, and in case of reads, we just read the data from anywhere it is, and we do not allocate the local L3 cache. For writes, in case of miss, we will need to allocate the local L3 cache, and in this case, obviously, something will be evicted from the local cache, which may induce some DRAM traffic. So basically, it is a good thing to monitor how many misses in the L3 cache you have for your DDIO transactions. So even if overall throughput is okay and you have a significant ratio of misses, anyway, it is recommended to check the DDIO latency. I will show how to do that. And just be aware that misses induce DRAM traffic and UPI traffic. And eventually, it also wastes platform power. So from all of the, from this perspective, so if you will look not only on the throughput, but also on latency and DRAM UPI traffic, it is better to have as many hits as possible. And a couple of words about MMIO accesses. So this is the primary technique for accessing device memory. So MMIO read is translated into outbound PCIe read, and this is the most expensive IO-related transaction from the core perspective, because every read requires completion. So all the time core waits for this completion, it is just stalled. So it is recommended to avoid MMIO reads on the hot path when the bulk data movement is done in your application. Otherwise, the throughput might be significantly limited due to these long latency reads. And MMIO writes is they are translated into outbound PCIe writes, and they are less costly, but still core needs to wait for some acknowledge from the platform. So you need to just minimize these MMIO writes and perform bulk data movement with Intel DDIO transactions. And usually MMIO writes are used just as some control operations, for example, to make some doorbells, writing something to device register to notify the device that we have some new job to process, and so on. So just try to minimize MMIO writes and avoid MMIO reads. And actually, it is possible to avoid MMIO reads at all. And let's see how these DDIO and MMIO requests are utilized in, for example, in storage applications. So in this example, we're looking at some storage application that makes pure reads from NVMe drive. So we have here CPU with the DRAM, and in memory we have 2 queues for submission and completion, and these queues are cached in the local L3. We have data buffer where we expect the data to arrive. We have some core that sends the IO operations to this SSD, and on the SSD side we have submission and completion queue doorbells. So these doorbells are mapped into the MMIO space. So these doorbells are accessible by the core. So let's see how this pure read is made by the core. So basically, this is the read from application perspective, because the application reads something from the SSD. But at the platform level, as you will see, we have multiple different reads and writes, right? So first, core prepares some job descriptor, and it writes this IO common descriptor into submission queue, and it starts polling the completion queue to see, waiting for the job done by the SSD. And core notifies SSD that this new piece of job is available by making the outbound write to the submission queue. And then, so device sees that there is some new job, and in the common descriptor, it goes to the submission queue and reads the common descriptor from the submission queue, and this is done by inbound PCIe read. And then device sees the address in the memory where the data is expected to be, and it writes the data into by this address into the CPU memory. And here we see inbound PCIe write, and then device writes the completion to the completion queue, where the core is polling, expecting some bits of the completion queue element to be changed. And at this moment, core detects that completion is done, and eventually it moves the completion queue tail pointer or head pointer by writing the by making the outbound write to the completion queue doorbell. So as you can see, to make just one pure read from application perspective, we need to make outbound two outbound writes, one inbound read, and two inbound writes. And actually, it also depends on the size of the data itself, because the integrated I/O controller talks to the L3 cache with the cache line granularity. So if, for example, if you want to write 128 bytes, it will be broken down into 2 cache line write requests. So each read is translated into multiple different transactions at the platform level. And as you can see, we don't need outbound reads here at all. So no such expensive operations are required. So let's talk about how to analyze performance of platform I/O. So for observability, at the platform level, we have thousands of Encore performance monitoring events, which are incorporated in the Encore performance monitoring units, which are assigned to the I would say to most of the logic on the platform. So we have PMUs in I/O controller, in the L3 cache controller, in the memory controller, and so on. So you can find the descriptions of available Encore performance monitoring events in the dedicated guide, but it appears quite challenging to make performance analysis using just the row counters, because it actually requires quite a deep knowledge of what's happening at the platform level. It requires you to understand what exactly stands behind these events, and because you will need to pick the right ones, you will need to somehow interpret the results. So because of all of that, it appears quite challenging. So Intel VTune profiler builds performance metrics and some methodology upon these Encore performance monitoring events, and gives you topology-aware top-down view on the platform I/O. So you get the data not for these PMUs, but you can attribute the metrics to end devices that you have. For example, if you have storage application, then you will be able to see how effectively your NVMe drive talks to the CPU, for example. So in this talk, we're going to discuss how to use VTune to analyze performance, not looking at the raw events. So VTune has different analysis types for different purposes, and I'm going to talk about input and output analysis. It provides Encore and device-centric view that helps you to locate performance bottlenecks of your application at both hardware and software levels. So we have two types of metrics. The first one is based on hardware events. So these metrics are application agnostic and device agnostic. So you can analyze DRAM, UPI, PCIe traffic, and see the details of this PCIe traffic, including DDIO and MMIO traffic. And from the software side, you can get some API level statistics for DPDK, SPDK frameworks, and for Linux kernel I/O. So the full set of input and output analysis metrics is available for Intel Xeon processors, and the analysis is enabled for Linux and FreeBSD. So let's take a look at how it looks like in the VTune. So in this first example, we have result captured for SPDK application that interacts with two NVMe drives, with two NVMe SSDs. So the input and output analysis starts with platform diagram. This is the topology picture that shows you that shows you all the sockets your processor has. It shows which devices were active during the collection run, and it shows you some utilization metrics on top of this picture. So for devices that were active in the tooltips, you may find full description of these devices, device capabilities, and device status. And the mismatch of these two attributes is reported as an issue, because in case if your device is configured with, for example, half available width, it may significantly limit throughput and might be the reason of performance issue. Also, yeah, you can detect a lot of topology related problems just looking at this picture, right? So you see here DRAM utilization. You see how it differs across the sockets. For example, in this case, all the memory was allocated on the socket 0. So I see that I have bandwidth only here. We see the application affinity, because when you run the analysis against your application, for example, attaching to the running process or launching the application, all the numbers will be filtered out for this particular application. So I see that in this case, this SPDK application was running on socket 0 as well. And I had two NVMe SSDs, one at each socket, which might be not really optimal. Probably I'll need to move both SSDs to the socket 0, where I have DRAM and cores, because in this case I have some UPI traffic that definitely makes transaction latency higher. So let's quickly discuss what utilization metrics we have here. So we have effective PCIe link utilization. So this is not the full PCIe utilization, because this ratio shows you what portion of physical bandwidth was spent on data movement. So it does not take into consideration the overhead, like TLP headers, physical encoding. So it's just the payload size, the total payload size, divided by available physical bandwidth. So in this case, obviously, this metric cannot reach 100%, but it is a good indicator of how far from the limit you are. So average physical core utilization shows you how many physical cores are utilized by your application in terms of CPU time. Cross-socket link utilization, it is basically UPI link utilization in terms of active clock ticks. And DRAM utilization is the ratio between observed average DRAM bandwidth and estimated maximal DRAM bandwidth. And the other example is for SPDK example that works with CBDMA accelerators. As you can see, we also can capture performance data for integrated accelerators. In this case, we have no idea, like we have no PCIe attributes reported by the devices, because they are not pluggable, they're integrated. So in this case, we just show average total IO bandwidth for these accelerators. And in this case, I have higher UPI utilization because I have higher traffic. And again, all the cores are running within a single socket, and probably this topology is not really optimal because yes, we have quite high utilization of both DRAM and UPI, which might be avoided if I'll keep everything locally. Okay, let's switch back to the SPDK application that interacts with the SSD drives. So after the topology is examined and you see like the high level picture of how your application is executed at the platform, then you can go to detailed PCIe metrics. At the summary tab of the result, you will find the PCIe metrics summary, which is the summary for the whole platform, like for all the sockets, for all the devices that were active during the collection. Here you will see the itemization of the PCIe traffic, like how many inbound reads and inbound writes you had, how many MMIO reads and writes you had, and at the second level you will find the average latency for inbound requests, which is a good indicator of the issue. In this case, we have quite high average inbound PCIe read latency, but I would say in this case we were close to the limit of SSDs, so probably we were just, you know, at the end of the this hockey stick, right? So when we were close to the throughput limit, the latency goes up. At the second level of for DDIO metrics, you will also see the ratios of hits and misses in the L3 cache. In this case, I see 100% misses of reads and writes, and also there is the ratio of write transactions that experienced CPU IO conflicts. So basically, latency might be elevated due to two things. We either have the miss in the L3 cache, and this miss is addressed with you know, with reading the data from the remote memory subsystem or local memory, which will have a little different latencies. And the other case why latency might be elevated is CPU IO conflicts. This is when IO controller has some contention for the cache line with some other agent like core or another IO controller. So this may take place in the applications that, for example, have polling communication model. When a core polls for the data that is getting modified at the same time by the device. So at this point, we may have some contention for data, something like the false sharing, but between IO controller and some other agent. So as I said, this is the summary for the whole platform. And if you want to see the breakdown by end device, click any metric in this metric tree, and you will be navigated to the per device metrics. So here you can see both first and second level metrics. For example, I see here that I have 2 drives, and basically when in summary I see that I have 50% DDIO misses. Basically all of these misses go from one of 2 SSDs, right? Because I see here that one of them that was local to the allocated memory and to the cores, it shows 100% hits, and the second one, which is at the remote socket, it shows 100% misses. And as you can see, we have a little elevated average latencies for the second drive that sits on the remote socket. So both read and write latencies are a little higher. And you can have the overtime view for the bandwidth. So you can see per device inbound and outbound PCIe bandwidth. again, you see that both my drives are reported here, and you can see the overtime DRAM bandwidth with the breakdown by channel, and per link UPI outbound traffic, and you will also see here data and non-data optimization to see how much data is moved and like snoops between the sockets. And as for MMIO accesses, we have a workflow to locate where in your application these MMIO accesses go from. So if you see that you have non-zero MMIO read traffic or some significant MMIO write traffic, you can see which functions of your application induce these transactions and to which devices these transactions go to. So in this example, in this summary, I see that I have 2 NVMe drives. I see which functions perform MMIO reads and writes, and I see what is the source file where these functions are defined. And when I click any of these rows here, I am navigated to the bottom-up pane of the result where I have call stacks that lead to these particular reads and writes from the device memory. So in this case, I see which function, what was the sequence of function calls that led to MMIO write. And going further, you can again double click this function and go to source level view and see at the source level where these MMIO reads and writes go from. In this case, I see that like 90% MMIO writes were induced by this particular line in this function. And eventually, let's talk about SPDK level statistics. So VTune statistics collection is integrated into SPDK framework. So when you enable the statistics collection at the compile time of the SPDK, you'll be able to pick dedicated checkbox in the VTune. And then for your SPDK application, you will see a bunch of different metrics for IO operations, for data read and written by the application. And you will also get histograms for throughput and latency. All the data can be broken down by the block device and the thread that talks to that block device. And the joint exploration of these API level and platform level metrics gives you a better understanding on how effectively workload utilizes the hardware resources. So let me demonstrate that on this simple example. So let's assume that we have this simple application that makes pure reads from the NVMe SSD. And let's say I'd like to understand whether I have as many MMIO writes as I need in my application. So I'm just investigating, like, can I potentially reduce the number of MMIO writes? And I have some understanding on how the application works at the platform level. And so I'm going to show you now how to make sure that your expectations are met, right? And that you do not use extra MMIO writes for traffic processing. So in the collected result, you can find the full outbound PCIe write bandwidth. You can see how many reads your application made, and you know the collection time. So from these 3 parameters, you can easily calculate the number of MMIO, like how many bytes were written through MMIO for each application read. So in this case, for these numbers, I have 8 bytes for each IO operation. And the next question is, does this match the communication model of my workload or not? So in this case, it matches, because for each IO operation, application makes 2 doorbells into submission and completion queues, and the doorbell size is 4 bytes. So this is exactly 8 bytes for each IO read. In case when you see that the number of bytes written through MMIO is much higher than you expect, you can, as I showed, just drill down into the MMIO access like heading and see where these excessive accesses go from. So this is how SPDK level and platform level metrics can be used jointly. And eventually, a couple of words about working with row events. So if you think that information is not sufficient in your analysis, you can see the detailed explanation of what events might be helpful for some deep analysis of the platform activities. Just follow this link. This is the presentation from our previous summit. And with this, you can customize input and output analysis by adding more on-core performance monitoring events. And then you can get even a per device view for these events when it is applicable. For example, in this case, I can see the row event counts for my SSD, like for both of my SSDs working in this application. So thanks a lot for your attention.